Welcome to a code report solution video. In this video, we're going to be going over the solution to problem 3 from topcoder SRM 732 division 2 entitled TheFlippingGame2. So the problem statement is here. It's quite lengthy and I'm not going to read it. So if you'd like to pause the video and give it a read, but conceptually this problem isn't that difficult. So I'm going to skip straight to the example and explain the question there. So essentially we're given three inputs for our function, two integers, one that represents the number of columns and one that represents the number of rows. And then we're also given a vector of strings which represents our board. And so on our board, we're either going to have tiles with their black side facing up, tiles with their white side facing up, or squares on our board that don't have a tile on them. So that's what the E stands for empty. So for the B, that means that the two-sided tile, that one side's white, one side's black, the black side is facing up. And so the game is played by first choosing a single color, either black or white, and filling that in for all of the empty tiles. And then once you've done that, you take turns one at a time. So it's a single player game, and basically what happens is you can flip over a tile, and when you flip a single tile over, any adjacent tiles that have the same color will also get flipped. So there's a cascading effect that takes place. And the question basically asks, what's the minimum number of flips that you need to perform, or terms that you need to perform, in order to get the board all one color? And note that the initial turn when you are filling all the empty squares on your board with tiles also counts as a turn. So let's take a look at a simple example. So in our example, black and white doesn't really work well to show the empty, so we're going to use blue and green. So this is sort of a colorful representation of our board that we're given here. And so in this example, on our first turn, we are going to fill the empty tiles with their blue side facing up. So this gives us one turn. And so now what we do is we choose any tile on the board, and we want to try and play optimally. And we're going to flip that tile over, and any sort of tiles that are adjacent or adjacent to those tiles with the same color are also going to flip. So if we flip the middle tile here, this will turn green, and then all these blue tiles will also turn green. So that's another turn, and if we flip the middle tile again, all of the green tiles on the board are going to turn blue. So at this point we have a board that has all the same color, and we did it in 3 turns, which is going to be the optimal solution. So there's a number of different ways you can get the optimal number of turns, but that was just one of them. So let's take a look at another example. So this is a 4x4 grid. Once again, we've got tiles with the blue side facing up and the green side facing up. In this example, we'll fill the empty ones on our first turn with green tiles. Then on our next turn, we'll flip any one of these green tiles here to turn them blue, and that'll take us to 2 turns. And then we can flip any one of the blue tiles, and that'll turn all of those tiles green. So once again, we were able to get to a singly fully colored board in 3 turns. So conceptually pretty easy to understand. So how do we solve this? So going back to our original board, the way we're going to solve this is with something that I'd call a layered flood fill. So it's a modified flood fill that works by using a priority queue in order to sort of explore your board. So if we start, we're going to choose a tile to start with in our top left corner, and we'll call that layer 0. And then what we're going to do is look at all of the valid adjacent cells. So we'll check up, to the left, to the right, and down, and if those exist on our board, we're going to check if it has the same color or a different color. If it's got the same color, then we're basically going to add that to our priority queue with the same layer. So if this was a blue tile, we'd add it to the priority queue with the same layer. But if it's a different tile, we're going to add 1 to the current layer and call it our next layer. So let's say this is tile A and this is tile B and C. When you look at them, it'll see, well, they don't have the same color, so we'll add these to our priority queue, and we'll add them with 1 plus our current layer, which is going to be 1. So note that we want to process the tiles that we're adding to our priority queue in order of smallest to largest, because as we explore our board, we're going to get higher and higher numbered layers. So by default, a priority queue is a max heap, and that means it'll process the largest item. So in order to process the smallest layers first, we need to negate our layer. So when we push our tiles with the layer that corresponds to each tile in, we have to negate the layer. And so then we'll pop off sort of our first tile that we looked at. So then we're left with these two tiles, and then we'll look at tile B first. And so we'll look right and we'll look down. We'll call this tile D and tile E. These are both the same color, so we'll add these with the same layer, and then we'll just continue to do this. So all of these green tiles will end up having layer 1, then these two blue tiles will end up having layer 2, and then the final green tile will end up having layer 3. And this will basically get us the minimum number of flips. And the way you can sort of think about this is that if this was a circle with rings, we want to find sort of the innermost ring in order to optimally flip these. So you can think of sort of switching the colors, or you can think of just counting the number of layers in a sort of ringed map. So here we only have slices, we don't have like a full circle, but that's the way you can sort of conceptually think of this problem. And so here I've sort of outlined the different layers. Here's our first one, our second one, and our third one. But here this would give us 4 turns because the initial turn was filling these tiles green. So the optimal one would actually look like this, starting in the middle, not starting in the top, and then both the blues here are going to sort of count as the first layer, and then this green one in the bottom corner will count as your second layer. So all we have to do with this layered flood fill algorithm is combine exploring the map by filling it with blues initially or by filling it with greens initially. That's for the empty tiles. So we have to try both of those. And then how do you choose the optimal tile? Well, because the parameters in this problem state that your grid is going to be at max 20 by 20, we can actually just check every single tile as a starting tile. So check both blue and green for filling the empty tiles, and then check every single one as a starting tile and perform our layered flood fill from that position, and then just take the minimum of all of those combinations, and that'll solve this problem. So let's take a look at our code. So here is our function, our first function, and it's just basically taking our 2 integers and an m, so that's for our height and our width, and our vector of strings, which represents our grid. We're initializing an integer called minflips, which is going to be our answer at the end of the day. Note here we're adding a 1 to it because the special turn counts, but in our calculations we're only going to be counting the number of flips or layers, you can think of it. And here's a small range-based for loop that's just basically filling our grid X here. So we're making a copy called filled grid, and then we're using another range-based for loop and the replace algorithm for each row in our grid to fill an E with our color. So first we'll try by filling it with the black, and then we'll try by filling it with white. And for each of these, we're going to make a call to the explore function and pass in the same parameters, except for X. Now we're going to pass in our filled grid, and then we're going to explore and calculate the minimum number of flips, or the minimum number. So let's take a look at our explore function. So this is a pretty big function, but let's walk through it slowly. So once again, we have our height, our width, or you can think of as the rows and columns, and our grid, which is a vector of strings. So we're initializing what we're going to return at the end, min flips, and we're setting this initially equal to just the maximum integer, which is roughly 2 billion. And then we're declaring a 2-dimensional vector, which we're dimension it, and we're filling the initial value for each of our squares in our 2D grid to be -1. Then the 2 for loops here are for checking the starting position. So this is just starting from the top left and then the tile to the right of it. So it's going to perform your layered flood fill for each of the starting position. That's what SY and SX, starting Y and starting X, stands for. At the top, we just have an initialization of our explored 2D vector because after each iteration of the inner for loop, we're going to have modified it, and so we need to reset the values to -1. Here we're declaring our priority queue, which we're going to use to store the tiles and the layers that we need to process. So note that it is basically we're storing 3 values. That's why we have a pair of pairs. The first value is our layer, and the second and third value are the X coordinate and the Y coordinate of our tile. And this variable here, integer max flips, is for keeping track of the maximum number of flips or the maximum layer in our explored grid. So the final tile that we finish exploring might not be the maximum layer in our flood fill, so we need to keep track of that. Then we set the starting tile to be 0, layer 0, and then we push this and the 2 coordinates into our priority queue. And then while our priority queue is not empty, we're going to perform the following. So extract out CF, which is the current flip, and then the current Y and current X just from the top of our priority queue, and then pop that off. Set our max flips equal to the maximum of its current value and the current flip or the current layer value. And then we're going to do our flood fill. So this is the classic loop where we're looping I equals 0 to I less than 4. And we're calculating the X and Y coordinates of the next tile. That's what the N stands for. The next tile that we're going to look at. So dy and dx are just deltas to get us from our current tile to the next tile. These are declared outside our function, but you can see them here. So this is just a combination of 1s, 0s, and -1s to get us looking up, to the left, down, and to the right. So once we do that, we check to make sure that our next y and x aren't outside our grid coordinates, so they're not exceeding the height and width or aren't less than 0. Once we verify that that's true, we come here and check, have we checked this before? And if we haven't, then we're going to come in here and calculate the layer of this tile. So we're going to set this equal to the current flip, CF, or the current layer, and we're going to add to it whether or not the current tile that we are at is equal to, in color, so that's what the grid is storing, our next tile. So if these are the same, this is just going to return 0. But if these are different, this is going to satisfy this condition, return true, and that'll convert to a 1, and then we'll get a new layer. And so once we've done that, we're going to store that in our explored 2D vector. We're going to negate that layer and push that in plus the 2 coordinates into our priority queue, and we're going to do this for all 4 directions, up, down, left, and right. And once we do that, we're going to come back to the top of our while loop and continue to do this while we still have tiles or squares to process from our explored grid. And once we finish this loop, we're just going to set min flips equal to the minimum of its current value and the maximum flips that we calculated from the starting position. And once we finish this for every starting position in our 2D grid, we're just going to return minimum flips. And so the last thing to talk about is time complexity. And because we're going to be traversing the grid, it's going to be width times height, but we're doing this for every single starting position. So it's actually going to be big O of width times height squared. As always, if you enjoyed this video, hit that like button. Make sure to follow me on Twitter for reminders 30 minutes before contests start. You can find all of the code that I use in my videos on my GitHub page. All of the links are in the description down below. And finally, if you want to make sure you don't miss any of my upcoming videos, make sure to hit that subscribe button. Thanks for watching, and I'll see you in the next video.